Okay, so now we have chapter 11, development length. Okay. So this has to do more about detailing and how you are going to cut or leave your bars in the same length. So those are things that are going to be done through this chapter. Additional stirrups may be needed depending where you cut bars. And then you have splices, how to do the splices, how you need to put stirrups on the splices. Sometimes you have to. Okay? So all that will be developed on this chapter. Okay? So let's look at the beginning and why do we need this. Now the reinforced concrete works because the bars bond to the concrete. Okay, and so they become one material. If that is not possible, then the bar will slip, and then it will not work as one. All right, so that's the key thing in there. The problem with the idea of this chapter is that you need to have a certain length of your bar. Otherwise, your bar will never develop the stresses that you need, especially that Fy. All right. And if the bar is too short, the stresses are going to be higher, and then that could cause splitting of the bars or splitting of the concrete. Excuse me. Right. And so that's why we need to look at this development length. Okay. So as I said, everything is assumed that everything works together. If it doesn't, then the bar simply slips, and then there is no stress in the bar. Okay, and so therefore the concrete will crack. Okay, because the bar is not working with it. Okay? So it needs to pick up stresses, so therefore it has to be that way. So it had to be there. And now we can use smooth plain bars, right? But that doesn't work very well. Okay. You need to really have an anchorage. That means you need to develop a hook at the end of the bar. If it's plain, you have to attach it to another steel member, maybe welded to a steel member. Otherwise, it will not work. Yeah? Now, smooth plain bars, they develop this chemical adhesion, but they also have the mechanical friction, and these are not good enough. Okay? So what people learn with the years, right, after starting with one kind and then try another one and another one, they'll learn that if you put on the bars some ribs or lugs, okay, then that works much better. And this created what is called the deformed bars, okay, because they have those little indentations there. So those are the lugs that you normally see in the rebars. So the rebars are not plain. So the concrete kind of gets stuck in here, right? So it develops an additional force. But then at the same time, that creates this force, right? Which you look at this in this direction, which is this one right here. So we're looking at the bar. So these forces are radial forces that are pushing the concrete. Okay? So if you don't have enough cover, right? Then that could cause spalling of the concrete. You can have a crack develop there. Okay? And so that's why it's the importance also of having enough cover over the bars in order to prevent these radial forces from creating those splitting or splitting cracks in the concrete. Okay? So what you can see here is that the different kinds of splitting, it just varies. Okay? It can be this case where the cover distance from the bottom is smaller than the cover distance on the sides and the distance here in the middle. Okay. On B, the half of the spacing of the bars, right, is smaller than the bottom part. The side is smaller than the bottom part, so all these tends to crack that way. Now here you have the side and the bottom being smaller than half of the distance between bars. And so in that case, your cracks starts on those on the bottom or on the side. Okay? So there are different types of crack initiation that will happen depending on the cover that you have around your bars. Okay? All right. Now these cracks, of course, they start by doing a little bit of cracking, but then with the time passes, the cracks kind of connect each other, right? So they connect, and now you got a section of concrete that could completely fall off because it has crack on all four sides. Okay? So it starts by being first a delamination. Okay? So that means it's no longer bonded to the concrete, to the bar. Okay? When you tap on it, it sounds hollow because it's delaminated. All right? And then after that, it will spall. Okay? Now, another thing that could happen also is the pull-out failure without splitting. Okay? And in this case, the lugs or protrusions that we have in the bars, right, will simply fail on bearing, and the bar will simply be pulled out. Okay? So we have then to have enough embedment length. I mean, that's what really is the thing. Okay, so you need to have enough bar embedded into the concrete, okay, to develop the yield stress. And this, of course, starts by looking at the critical point. So here we're only putting a point load just to simplify it, right? You always had the weight of the beams and all that, but by just ignoring the weight of the beam, you only got the point load. So this is your point of maximum moment. That means this is the point of maximum stress. So the bar to the left and the portion of the bar to the left and the section to the right, they have to be able to develop this stress, this Fy. Now this one is longer than this one, so then we worry only about this one. So this one has to have enough length, okay, to develop the stresses in the bar. So you apply a force, right, and you have to have enough length so that will happen. Okay? This is something like I think I have something here. Yeah, can I have that here? It doesn't matter, I guess. No, it doesn't matter. So I guess we'll keep doing it. One more time. All right. So you apply this, you got this stress, yeah, at the maximum point, you get this Fy. So this length has to be enough to develop all those stresses. Now the stresses develop, they're higher at the end, right, with the stresses being applied, and they go less and less until you get to zero, right? So there is no stress right in here pretty much. So most of the stresses are developed in this section. So notice that the stresses are developed on the surface of the rebar, right? And so that's an important concept because we're going to use that. Okay, so it's in the surface of the bar that we're developing those, okay, to balance the actual stress caused by a tension force in the bar, right? All right. So if we do that, then you get the tension force. It has to be equal to the stress on the bar. Okay. Well, the stress, those little arrows that I show you, right, are represented by this. This is now a bond stress at ultimate because we're looking at failure. So that's why the U. And it's average. Why is average? Because as I show you here, it varies. Okay? It varies. It's not uniform. Okay? So we need to have an average bond value. Okay? So we take an average. Now if we take the average stress, and remember what I said is apply on the surface, right? So you think about a cylinder, what is the area of the surface of a cylinder? Okay? The area of the surface of a cylinder is given by the circumference times the height of the cylinder. Okay? Okay. For a bar then, the circumference is pi times the diameter of the bar. Right? And the height of the cylinder made by this bar is the development length, okay, LD. Mm-hmm. So this is then the surface area of the bar. Okay? So that's what that term is. Okay? So that term represents then only the surface area. So it's the circumference multiplied by the length. Okay? So it's your surface area. So we take that, multiply by that gives us a force, of course, and we make the T equals AB times Fy, and then we solve for LD, and we got a formula, right? So, gosh, everything is great. We got a formula. Very easy. So, we know dB, we know Fy, we know this, but how about this guy? I mean, that's the guy who's going to cause the problems, okay? We don't know that guy very well. So, we have a problem with that one because it depends on the diameter of the bar. Depends on the covers, either side, bottom, or top. We've seen that, right? So depending where the crack is going to step. Depends on the embedment length. Depends on the area of the reinforcement. Depends on the yield strength of the reinforcement. Depends on the spacing of the reinforcement. Depends on the type of bar. Is it coated, no coated, right? Depends on where it's placed within the member. Okay? Depends on the type of concrete, normal, lightweight, right? And depends on transverse tension cracking. Oh, that had to do with shear. Okay, so lots of things there on this little guy. All right, and it's very difficult to evaluate. And so what people did, I mean, they just went run tests, lots of tests, right? And they came up with some formulas. Right? So the formula here, which is given in your code in section 25424, is the general formula, okay? And it's this one right here, okay? So if you look at it, notice that we compare it to this one, right? We got a D sub B, we got an Fy, and we got a 4 here. So we got the D sub B, we got an Fy, and the 4 is kind of in here, right? All the rest, right? All the rest are the modifications that we're putting in order to account for all the factors that affect your bond strength, right? So that's bond depends on diameter of the bar, covers, embedment length, area reinforcement, yield reinforcement, spacing reinforcement, type of bar, right? Depth of concrete, that is location of the bar, type of the concrete, normal or lightweight, and shear. Okay? And so all that is in here based on tests. So all the little guys are simply correction factors. Okay? So the top, F side T, is a location factor, right? One of the factors that affect the bond. So if your horizontal bar, your longitudinal bar, is placed such that no more than 12 inches of fresh concrete is cast below the horizontal reinforcement, right? Than more than 12 inches is cast, then you got a factor of 1.3. So you need more development length. In other cases, you do 1. Now, why we call it top reinforcement? We normally call it top reinforcement because that is your negative bar, right? Negative moment bar. That's on the top. And there is concrete below that one, right? So that's the only way you're going to get more than 12 inches below a bar, right? If it's a positive bar, it will be at the bottom, you only got the cover. The cover is only, 2.5 inches. You never get the 12, right? So it's the negative reinforcement, right? The negative moment reinforcement that will have the potential for having more than 12 inches. Okay? Coating. Okay, well, I mean, that one is kind of sort of obvious, right? You put some kind of coating on a bar, right? You will change the friction, and therefore you will change the behavior. So if it's epoxy coated or zinc and epoxy, dual coated, right? Then, and with clear cover, less than 3D sub B, okay? Or clear spacing, the spacing between the bars, less than 6D sub B, you will have to use a 1.5. So it's larger, right? For other cases of coated bars, 1.2. If there is uncoated, simply 1. Okay? The product of these two, psi T and psi E, shall not exceed 1.7. And that only happens when you do a 1.5, 1.3. Okay? Now the size S has to do with the size factor, right? The size of the bar. Smaller bars need less development length, so 0.8. Larger bars need more development length, that's a 1. Okay? The new term, and this is for those of you that are took this before, this right here is a new requirement introduced in 2019 code, and it has to do with the yield value of the bars, because now we have 80 and 100 officially in the code, right? And so you got grade 80, you need more development length, and of course grade 100 will need more development length, right? So 1.30. Now lightweight concrete has always been there, but this has been simplified. Any kind of lightweight concrete 0.75, normal weight concrete 1. Okay. Then we also have on this formula we have this part, right? C sub B, KD sub R. So we need to look at those. So what is C sub B? C sub B is the spacing or cover dimension. So this guy is the one that's going to look at, right? Look at the potential crack. What crack are you going to get? This one, that one, this one right here, which one, right? So that C sub B is going to look for this. Okay? And so that's why the definition of it says it is equal to the lesser of either A, the distance from the center of the bar or wire to the nearest concrete surface. That is your side cover, right, to the side, or the bottom cover, right, to the bottom, or you're looking at top bars to the top cover, right, to the top face. Right? And 1/2 the center to center spacing of the bars or wires being developed. Okay? Being developed. Okay? And so this is important, because it says center to center spacing of the bars or wires being developed. Okay? So it's not exactly the spacing of the bars. It's the bars being developed. So which ones are you trying to develop? Okay? Yeah, you're going to develop all the bars, then yes, it's the spacing of the bars. You're developing certain bars, then it will be those that you're trying to develop. You need to look at the spacing of those bars. KT sub bar tries to measure the reinforcement for shear. So this one tries to capture the shear issue, right? And it's giving us 40 times AT sub r divided by S divided by N. So AT sub r this is where it gets difficult. Okay? Total cross-section area of all transverse reinforcement which is within the spacing S, and which crosses the potential plane of splitting through the reinforcement being developed. Okay? Okay. So that's when it gets there. So here we have some idea here of what this means. Okay? For example, so ABV, we're going to call that one the area of the shear reinforcement, which is your transverse reinforcement, okay? So it will be 0.11 for number 3 stereos, 0.20 to number 4 stereos. So this is what you've been using, okay? Now, if you have a vertical splitting, as shown here, right? Then there is only one leg, right? One leg of the stirrup, well, in this case, the bottom portion of the stirrup, that crosses those cracks. Therefore, your AT sub bar should be ABV. You have a horizontal splitting like this, right? Now you have two legs, right? That are crossing the cracks. And so you multiply by 2. Here, you have cracks on the side and cracks on the bottom. So now you got 3, right? This leg crosses that one, this one crosses those 2, and this one crosses that one. So we got 3 areas of reinforcement. So that will be then 3 times. However, most designers used to, okay? Because it's kind of, okay, can you prove that really you are having 2 cracks like that, right? And then on the last one right here, for example, where you get interior legs, right? You got like these double stirrups. You may have cracks like this, and so in that case you got 4 legs. Okay. So 80 bar then is kind of the difficult one. Okay, had to find it. S, center to center maximum spacing of transverse reinforcement. So this is your S or your stirrups normally, yeah, that you're using within that LD. Okay. Now LD may be happening near the center of the beam, maybe at the end of the beams, right? And so you need to look at the stirrups that you have on those locations. Okay? And then N equals the number of bars or wires being developed. Okay? So how many bars are you developing? Now the good thing is that the code says, well, I mean, it would be conservative. You take this guy equal to 0. Okay? So you're happy with that, and you don't need shorter development lengths. You can assume that value to be 0, even if you have shear reinforcement. Okay. Now, in the case of grade 80, though, this is new, okay, because grade 80 is being added now to the code, or higher reinforcement, spaced closer. So you've got bars that are spaced closer than 6 inches on center. The code requires that transverse reinforcement be provided to maintain KT bar greater or equal than half of the diameter of the bar. So that means that this value here has to be greater than half the diameter of the bar. Okay? But that's only for that case. Now, even though you may have it and you do that, you still can use a 0 in your calculations if that's what you want. Okay. So this would be, of course, is the nominal diameter of the bar. LD is the development length that you're looking for. Your F prime C, of course, is the concrete strength, specified concrete strength at 28 days, and it cannot exceed 10,000. Okay. Another limit that the code has is, remember we talked about the possibility that it's not just a splitting crack, but maybe the bar pulls out of the concrete, right? Well, to avoid that, this ratio of CB plus KT bar divided by D sub B has to be maintained to less or equal than 2.5. You don't want it more than that. So if it exceeds that, you use only 2.5. Okay. And then you have a minimum development length, right, as 12 inches, 1 foot. Okay. So that's the minimum you can have. So that's the equation. That's the basic equation that we have, right? And then the code came out with these conservative values, right, to simplify some of these things. And it created a table like this, okay? And this one is presented in 25.423. So notice that is before the other one, because the other one was 25.424. And so some people think, oh, then this is more important. I need to do that first. No, the other one is really the key formula. The other one is this one right here, okay? Pretty much there. So these are simplifications, okay? And so the top here, so these are simplifications. So when you use these equations and these simplifications, you're going to get longer development length values. Okay? The top equations are using a value 1.5. Okay? For other cases, they're using a 1. Okay? So all these right here, notice that they don't have this C sub B KT bar over D because they're already using a 1.5. Okay? And so that's how they make this one. Okay? Right there. So you put here 1.5 in the denominator. That means the 3 cancels and the 40 becomes 20. So that's this one right here. Okay. And so that's what it is. So this one right here then have a value of 1.5 for that for your value here that we have defined. What it was, your C sub B. Oops. Wait a minute. We had the limit. I'm looking for the limit. Yeah, for this one. Yeah. So your confinement factor has been taken as 1.5, which is below this 2.5. Okay, so that's an assumption in there, and that's how they develop those formulas. These ones have a value 1. All right. So these are going to be more conservative. But in order to use these equations, though, you had to satisfy certain requirements. Okay? The first column here is for number 6 or smaller bars, and number 7 is for larger bars. So that's why there is no SIS, because that has been taken care of. Okay? And I think, so that's that one. And then, but you have to satisfy these requirements here. So clear spacing or reinforcement being developed, or any lap splice, no less than D sub B. Okay. So you cannot go below D sub B on your clear spacing. Clear cover, at least D sub B. In most cases we do that because we use 1.5, right? So we're good there. And stereos or ties throughout LD no less than the ACI code minimum. Yeah, I think most of the time we put them there. Right? Or clear spacing or reinforcement being developed or spliced no less than 2 D sub B, and clear cover no less than D sub B. This is easier to check. So this one right here is easier to check than this one because this one depends on the shear. But this one is a lot easier. All you have to do is 2 D sub B. Clear spacing. Okay. So you have number 8 bars. You need to have a clear spacing of 2 inches between bars. We normally do that, right? And the cover definitely is more than that, right? So we are good, unless you're using number 18 bars, right? And so we have those in there. So these are then the simplified equations that we have now in the code for this purpose, right? Now what I was looking for is I missed something here. You didn't know. I was looking at it. Now remember we have added the yield value, right? The bars. So now we have this G value here that needs to be maintained. So we have that. That has, because now we have either 60s, 80, or 100. So that's not been taken care. So that has to remain in the equation now. Okay? And so I should have done this. So that will be the same in all 4 equations. Okay? So these now represents your strength of the rebars. Okay? So all 4 equations have that psi g. That's new in ACI 318.19. Okay? It was not there on the previous code. So you learned your concrete, or you went in a class that had used the previous code. This value was not there, and you will be missing an important factor. Mm-hmm. All right, so now all the equations are updated, and there they are. Okay, there is one thing that the code allows for certain cases, not for all the cases, but most cases, is a reduction of the development length based on the amount of steel that is required and the amount of steel that is provided, right? In most cases, we put more than what is required, right? That's what we do. And so this ratio is usually less than 1, and therefore will reduce the length required. Now you can never go below the 1 foot though. Okay, the 1 foot stays 1 foot. Okay? You cannot use this one for the case of non-continuous supports. Okay? So that's kind of the ends, right? The ends of your beams. Where anchorage of development length for Fy is required. So you have to design it for that. So then you cannot reduce it. Where bars are required to be continuous. In some cases the code says you cannot remove these bars. I mean, they have to be continuous, okay? Especially for integrity, all right? So you cannot use this requirement. Hook, headed, and mechanical anchor deform reinforcement. Okay, we see that. We will see this in later, okay, what these guards are. Members on the seismic force resistance system that are in seismic design categories, your SDCs, C, D, E, and F. Now the code has added C now. C was not there before. Okay, so those are, and these are for piles, concrete fill pipe. We don't do much of that here, but the same thing. Okay, so in those cases you cannot use this. All right. So let's see an application here. Here, what you see here is a plan view of one of the ways that people represent slabs. Okay? So this is your slab, right? And they kind of cut it in half, right? And the top half shows your negative reinforcement. Notice that is bars on the top of the beams, right? And your positive reinforcement, right? Which is maximum at the middle, right? So you have that. And then people will label these bars. So this is bar E, bar F, C, D, all these different bars, right? And finally, they will come up with another view where they show you your bars again. So these are your negative bars, right? And then your bottom bars. It's matching the locations. And then you will have your bar scheduling, right? Well, you have I type A, bar A is in number 9. You can add the length, you have it, okay? And you put the spacing of the bar. And so then people will know, right? So that's what we have here, okay? So the different bars and the different spacing. So the spacing is a bar E goes from this one to this one to this one, okay? The spacing for bar F goes from this one to this one to this one, okay? And so that's how the spacing is specified. And that's what you have this here. Okay. So if we use the detailed equation, then we come here, Fy 60, F prime C is 4,000. So this one, they say that we have what? We have 1 inch cover, okay? Plan view. All right, so site T. Why is site T 1.3? Well, you have your negative bars that are here, right? And so these bars could have enough depth, depending, of course, on the thickness of the slab. This slab is 16 inches. So that means that definitely you got that, right? The bar is about, say, 2.5, maybe 3 inches. So there is another 13 inches or 12 and a half below this bar. So definitely there are 12 inches below these bars. So for the negative bars, which are these cases, right? Negative bars, we do have 12 inches below the bars. So we're going to use a 1.3 for those bars. Nothing about epoxy, so that's 1. Size is a number 9, right? Remember that 7 and up, 1, okay? 6 and below, 0.8. Grade or reinforcement, we're using 60, so that's a 1. Regular concrete, that's a 1. Product of site T and site E, 1.3, mean less than 1.7, okay. As I said, the only time it happens that you may exceed this is when this is 1.5 and this is 1.3. Okay. Now we need to find C sub B. Okay. distance from center of number 9 bar to its outside surface. Okay, they telling that the cover was 1 inch that was given, right? So we go to the center of the bar, we add half of the diameter because this is a slab, there are no stirrups. So all the thing you're going to add then is half of the diameter. Okay. Then we're going to do 1/2 the center to center distance between bars, right? And we're trying to look for the smallest possible. So we look then for the smallest possible spacings of these bars. And all the E's, D's, and F's are at 8 inches. So that's what we're going to use. And we're doing the top, right? So we use the 8 inches. And we get half of that, which is 4. Now we look at the 2. Okay, this one governs. And we're going to use that as our C sub B value. Okay? So what this means is that then our vertical cover, vertical splitting, is controlling the design. Right? KT sub R, we're going to assume 0 because it's slabs, right? No stirrups. Right? So this should be 1.128. So we go to find our confinement factor, right? And KT sub R is 0. We got C sub B. We got that is 139. Is less than 2.5. It's a good value. We use it. And we get 66.7. You can round it to 67 if you want. Right? Then you multiply this times the diameter and you get your development length. 75.2. Greater than 12 inches is good. So I said, okay, use 75 inches. Okay? So you can use 75 inches, right, for your development length in this case. Right. So how much is 75 inches? More than 6 feet, right? So yeah, development length is can be long. Right. Now here, what we're going to do is what most people do in offices. What they do is they develop tables already, right, for different cases. So we're going to keep the same reinforcement at grade 60, but we're going to vary the concrete, right, every 500 feet, and we're going to have assume different confinements, 1 and 1.5. So side T, we're going to say 1. That's this bottom bars, right? No epoxy. This could vary depending on the size of the bar. This one remains the same because we're doing only grade 60. And lambda is 1, and of course this is satisfied, so we're good. So when we're using the first value, the confinement factor equal to 1, right? And we replace all these coefficients, this changes to this. The only thing that varies is your size S, depending on the bar size, and your concrete. Okay? And so we have number 7 and larger will be 1, and number 6 and smaller will be 0.8. So that's how we change that one. Right? So we get 2 equations. And now we start changing the concrete, right? And taking the square root, right? And we get these numbers. So this is what people have a lot of times. So when you see in a set of plans, they will say, okay, your development length should be no less than 60 this should be. Okay? Or if they want to be conservative with both, they will say, oh, no. Your development length should be no less than 70 this should be. And that covers both. Okay? Taking care of that. Okay? So for most cases, that is conservative, but we're going to see a case where that may not be. But in general, that's what people do. They develop these tables and then they use these values to put them in the set of plans. There. You use a 1.5, your values are different. Okay, so that's why when you look at these recommendations in a set of plans, be careful. Don't just copy those because you can get different values depending on your confinement factor. Okay. And so one value takes care of all. That's not true. Okay? And sometimes it's used that way. Okay? So this varies. Okay? Varies a lot. Okay? So this is just the purpose of showing this is only to show you the differences. Okay? So 5,000 here, you got 51 and 64. 5,000 here, you got 34 and 43. Okay? So it's not one value for all cases. Okay. Next, we're going to look a little bit of the anchorage. The anchorage really has to do, and you have to make sure that you either have a hook, right, and you have enough length to, again, develop the stresses. Remember, you have to develop this Fy. So you have to have enough length where the zero value is growing until you actually develop an average value that matches this one, right? Otherwise, you don't have enough length. Or you can simply attach it to an angle, right? And here, of course, there is a potential that the crack will come right at an angle here too, and you will lose this corner. Okay? In there, so that you need to watch for that. Okay. All right, so that's our regular development lengths, straight bars. Okay. But we can use also hooks in tension. Okay. This will reduce the length that you need, okay, when you have a hook. And so the hooks have a different equation. This is new in 2019. Okay, it's a new equation. Don't use the old one. All right. And of course, it has some modification factors like we did for the other one. And again, lightweight concrete we know is 0.75. Epoxy coated, they give me one value, 1.2. There is a location value, okay, that has to do with the cover. Right? So for number 11 and smaller diameter hook bars that terminate inside the column. Okay, so you're going into a column with side cover. This is your side cover. Okay? Normal to the plane of the hook, greater or equal than 2.5, you will use a 1. Okay? Or you have a side cover normal to the plane of the hook, greater or equal than 6 times the diameter, then you can also use a 1. So notice that this one is you have to be inside the column. This one you don't have to be inside the column. Okay. You may be going to a wall, you may be going to something else. Okay. If you don't satisfy this, then you should use a 125. Okay. Then there is the confining reinforcement. Okay. And this has to do with the area of stirrups that are around the hook bar. Okay. So, ATH is going to be the area of stirrups that you provide within the hook length. And AHS is the area of the hook bars that you are developing. So if ATH is greater or equal than 0.4 AHS, or S is greater or equal than 6, this would be, you will use a 1. If you do not satisfy this, you will use a 1.6. They also introduce a term for the concrete now, a size C. Your concrete is less than 6,000, it will vary with the concrete strength. But if it's greater or equal than 6,000, it will be a 1. And in this case, you can use the reduction factor, but again, limited to the same cases that we have discussed before. After all these modifications, you cannot be below 8 times the diameter or 6 inches. So what are the general comments about these hooks? Hooks shall not be used to develop bars in compression. All right. So you have a bar in compression, the hook will not work. If the bar terminates at a discontinuous end, requires a hook for anchorage, and if the side cover and top or bottom cover, depending where it is less than 2.5 inches, ties or closed stirrups perpendicular to the LDH must be provided. Okay? So that means you have to provide stirrups right in here if you do not satisfy those requirements. And there are spacing requirements, right? That the spacing will be 3D sub B. Okay? But the first stirrup from the end of the hook should be 2D sub B. Okay? If you provide all that, then you can take this as a 1. Okay? And the code has a nice picture about this one, I believe. Let me see. So we're looking at 25. Yeah, we're in 25. That's good. 25. So code has all this good stuff here. These nice pictures now. Oops, I went past it. So I guess I had to go slow. Okay, maybe. So we were right there. Okay, this is close, but it's not. Right there. There you want, right here. Okay. So you go to this end, which is non-continuous, right? Notice that your first stirrup from the hook, right, 2D sub B, less or equal than 2D sub B. Okay? All the other ones greater than 3D sub B. Okay? So greater than 2D sub B, first one, greater than 3D sub B. Okay? So less or equal than 3D sub B, sorry. Less or equal than 3D sub B, less or equal than 2D sub B. Okay? And again, your covers are 2.5, 2.5 on the side. Okay? So that's what that one is talking about. And that's what this drawing is about. So first stirrup from the hook, less than or equal to 2D sub B, rest of stirrups less than or equal to 3D sub B. And this would be, of course, the diameter of the hook bar, not the other bars, the hook bar. Okay. All right. So you have less than 2.5, you definitely have to provide those stirrups. Okay. They are important in there. Stirrups are not required at the discontinuous end of slabs. So slabs, you don't have to worry about it. Okay. Because the slab itself being so wide, right, it provides enough concrete distance for the hooks. All right. Some detail requirements are shown here from ACI. So this is the same figure from your ACI. Actually, it says there ACI, right? So it's the same thing. Okay. And these are things standard, so most people know about this. I mean, the builder knows about this. Any contractor knows about the standards, okay, and what they are supposed to be. Okay. So these turns right here, you have minimum value. So it's not everything you want. It has a minimum. Okay. The extensions after you do the turn, right? Then the straight part of the member, 12D sub B. Okay. This is important because sometimes you say, oh, yeah, I want a 90-degree hook on my beam. But wait a minute. You got here 12D sub B, right? Plus the diameter here, 6D sub B. That's 18 times D sub B. So you have like a number 8 bar, right? That would be 18 times 1. That would be 18 inches. So you need to have 18 inches to put this one, plus the cover, top and bottom, right? So you need a beam at least 24 inches deep in order to recommend this, okay, for the number you are using number 8 bars. So be careful. This is something that people make a lot of mistakes. They say, okay, yeah, put a hook, but they haven't thought about how much they need. Okay, so that's very important. Okay, covers, as I said already, I mean, we got top cover, end cover here. This is an end cover, top cover. This could be there. Then you're looking down now into the column. So this is your column, and this is your beam. You're looking down on it. You can see your end cover, and you can see your side cover here, right? Side cover, end cover, right there. Okay. Okay, so let's look at the 11.3 example here. You got a reinforcement, right? Negative, and this is typical. You got a column and you got a beam, and the maximum negative moment is right at the face, right? So that means that this is your critical point. To the left and to the right, you need to have development length. To the right, I mean, there's no problem. You got plenty of beam. But to the left, you had to have development length. Well, to put a straight bar here would be very difficult, right? Especially you have like a number 8 or a number 9, right? We're looking at what? We look at one value that was 7 feet. You need a 7-foot column wide. You cannot do that, right? So that's where the hooks come in, okay? So we can use the hooks. And so we're going to do a 90-degree hook. And here there is no problem in putting a hook because it goes into the column, right? And so it's totally different. Mm-hmm. The side cover of the top bar equals 3 inches, and the end cover of the vertical leg is 2.5. Center to center spacing, 5 inches. Concrete 3,000, FY 60,000. So we got the equation here, all right? And we are going to have there, so this is the new formula, right? And you modify it, so your epoxy coated, which is here, is 1 because there is no epoxy coated, right? It's regular concrete, so lambda 1. But we have side R. They don't mention any stirrups along the length being developed, okay? And so there is no no stirrups, right? And then we also need to look at this side O. Okay, this is kind of new. This is new for this. So side cover 3 inches is greater than 2.5. That's all they say. If it's greater than 2.5, we can use a 1. So we use a 1. Your size C depends on the concrete. So we use 3,000. That becomes now a 8, right? And that's that one pretty much, right? The only thing I see duplicated here is this one. So I'm going to take it out, right? So you land there, and then we got this. All right. So we put the values, right? Put the values here, your FY, your coefficients, all the corrections, 0.8, 55, your lambda, your concrete. Always remember PSI, 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 PSI. 5/8 raised now to the 1.5. This is new, especially for those that have taken concrete before. This was not there before, so make sure that you have it, 1.5. Okay. So that gives me 7.9 inches. The limits are either greater, AD to B, or 6. Well, 6 is bigger, so 6 is the limit. We are putting 7.9, we say 8 inches, and we're good. Okay. Can we put 8 inches of hook? Well, yes, right? We got 16 inches here, and we take 2.5. So yeah, so we are good, right? So we can put then the 8 inches, no problem. So that's satisfactory. Headed bars and mechanical anchored bars. Headed bars are something that I started some years ago, okay? And they were developed because they help a lot with dealing with congestion. Okay? And so let me look for some pictures here for you, because now I cannot show you the bars like I do in the class normally. So I had to find them here. All right. So headed bars. So here's one type. See, they have those ends like that. Okay. So that, but they can be circular. It can be squares. Okay? You can have squares, right? And that's how they are used. Okay. And the purpose is that you're going to replace really the number of hooks. Okay. So it reduces the number of hooks. Okay. That's the whole intent of doing this, these headed bars. Okay. So you're using different applications. Okay. But still, I mean, you can see that even here, I mean, you still got Lots of bars in there, right? Oops. Well, A1 there. Yeah, they are showing anchor bars. So yeah, trying to avoid, this is the overlapping, so trying to do that. So some of those right here, right? Some of these right here where you have, so this is a joint, right? And so you don't have the hooks. See, that helps a lot, because with the hooks, I mean, you have extra bar that has to be bent, and that takes more space. Mm-hmm. And so that's how they're doing this. So this thing has an advantage of using these headed bars for the purpose of replacing the hooks. So you will not have all these bent bars anymore. You can just simply stop it and have your bars. So that helps with the congestion. Okay, and that's the good thing about it. Yeah. I don't see anything more interesting here. Okay, so that's good. All right, so we got those. And the bar shall conform to ACI 20.2.1.6 in ACI, right? And this is pretty much the regular requirements for your bars. Okay? So we have those right here. Headed deformed bar shall conform to ASTM A970. Okay, so every bar has its own standard, right? And so that's all they're saying. You need to satisfy the ASTM standard. Right? Okay. Bar size less or equal than number 11, because that's what's been tested. Net bearing of the head. Remember those circular areas, right? When you pull, when you apply force, right, then that circular area is going to bear in the concrete, right? That's the bearing into the concrete. So you want then the area bearing greater or equal than 4 times the area of the bar. Concrete normal weight, simply because those are the tests that have been done. Okay, there is not enough information on lightweight concrete. Clear cover for bar greater or equal than 2 times the diameter. That's your clear cover. Okay. And the center to center spacing between bars greater or equal than 3 times the diameter. Okay. So you satisfy your ASTM standards, then your formula is here. Again, for those that did this before, this is a new formula. It has now an exponent. It has a different coefficient. So be careful. Okay. We've already seen Psi modification factor based on coating. There is a P, right, which is based on parallel tie reinforcement. How many ties are you putting parallel to these bars? Okay. O is Psi cover and confinement. So this is very similar to the Psi P that we used previously. Okay. I don't know why they call it P, but see, now they call it P here and they call it O here. So that can make it a little bit confusing, but yeah. Then modification factor based on concrete strength. So we have the same thing. Okay. So there they are. Okay. So this one is how many ties are you providing compared to the hook. Okay, or in this case the headed bar. Right? And so we have that, and then of course the formula for the concrete, right? So that's the same as this one in there. I'm checking one thing here just to make sure. Yeah, it still says hook bar, so yeah, they haven't changed that, but this refers to the headed bar. Okay. All right, so these are your covers again. 2.5 is kind of the magic number. It's not something to remember, right? And that's pretty much it. So these are your modifications, all right? So again, you cannot be less than 80 sub B or 6 inches, whichever is larger. Now, how do you measure this? The development length for a headed bar goes to the face, the interior face of the bearing plate. Okay, little bearing plate. The cover, right? The cover goes here. Okay, so that's your regular cover. Okay. This one needs to satisfy 2544, which is not the same as your cover. So this one is the 2D sub B. Okay, so this value right here refers to this one. Okay, it's to the end of the bar. You need to have more or equal than 2D sub B. Okay. All right, so this one is your regular clear cover from chapter 20, but this one is at least 2D sub B. Okay. Cantilever, so your critical section, of course, is at the face, right? Now, if you are ending this into like a beam column connection, what they recommend is that you extend your bars, right, into the core of the column. Again, the code has some good pictures, and so let's look at the code here. 25. All right. So we did that one there. See? So what they mean by that is you want to get it inside the core. So this is your core of the column, right? You don't want to get it past. You don't want to interfere with the bar of the column, but you get it as close, all right? But get it inside that core. That's what you want, okay? In there. These are other requirements that they show you. You don't have any stirrups provided like these stirrups right here, right? And therefore you just have the bars going up, the other bar coming here. And then what happens is you can have this compression strut here causing you a problem. And so in that case, they want this length, right, from the face to here, to the right before the bearing plate, to be greater or equal than the D of the beam divided by 1.5. Okay. Now you provide enough stirrups, like this one right here, right? And then you can have this truss effect. Then that one can be less than D over 1.5. Okay. That's all they're showing you there. So those are kind of details. That's what I said. This is a lot about details. Okay. All right. So problem, we're going to do the same hook problem that we did here, right? This one. So we're going to do the same, but instead of using a hook, now we're going to use these headed bars. Okay. So we look at the modifiers, right? SAE, non-epoxy, 1. There was no indication of ties, right? However, we were given the spacing, right? And the spacing, if it satisfies this, then we can use a value of 1. And so we check that. They say the spacing was 5 inches. 6 times the diameter of the bar is 375. So we satisfy that, okay? So that means your psi P is 1. This one right here, remember that depends on the location, so it depends on your cover distances. We got 3 inches given, greater than 2.5, again, that is a 1. And then the concrete, we replace the value there, right? And it's 0.8. And now we put everything in the formula, and we get only basically 6 inches. We check the limits. The limit is 6 inches, so we should use 6 inches. And 6 inches should be enough to be there. Right? Now, you may not be able to use these 6 inches. You may have to use a bit more. Because of what? Because of these conditions, right? Are you providing these stirrups? Then you're okay with this, right? Or you are not, right? You are not providing those stirrups. Then you have to be greater than D over D divided by 1.5. Right? So you may have to increase it. Now, even though we find 6 inches, you may have 6 inches maybe from here to here, right? That will be your 6 inches, around there maybe. Okay? You don't want to stop there anyway. You want to take it all the way here. Okay? So right before your bar, put it inside that core. Okay? Very important to put it inside that core. So I would say, I would use, in the case of this, I would probably use a value, as a practical value, I will use 12 inches, okay, to make it inside that core. Mm-hmm. So for my example that we have here, right, I would say 6 inches may not be enough to actually put it in the core, right, because this is 16 inches, right? Where are we here? Yeah. So 16 inches that we have for the column, right? So we got 16 inches. If I'm going to do 6 inches, I'm going to be here. And so I don't want that. I wouldn't want to be here either, but if I do maybe 4 inches inside, that would be 12 inches, right? So 12 inches will put me right at the core in there, right? On that one. So that'd be a good compromise for this one. There's a practical application for this. Compression reinforcement, this is it remains the same. It hasn't changed from previous, so it's still the same. Value is limited to 8 inches, but you have two equations. You have to check both, and this is also kind of a lower limit here, so we have to check both values. Okay. And again, there are correction factors, lightweight concrete, 0.75 for 1, right? And then there is the confining reinforcement, right? So you have reinforcement that is enclosed by either a spiral, a circular continuous wound-tied, so we can do circular, with this would be greater or equal than 1/4. So that means you're using pretty much number 3s, and a pitch of 4, right? So this is not the true spirals that we have seen in column, right? Because 4 inches is a lot, right? But you have kind of the same, similar. You can use this factor. You can use number 4 wire or D20 wire tires, right? Satisfying now section 25.7.2 of the code, a space at no more than 4 inches. Or you can use the hoops, right? So not spiral, but hoops, so the circular ties, right? Satisfying 25.7.4 again, with less or equal than 4 inches spacing. You can reduce the length that you need for those compression, for the development length in compression. Okay. All right. We'll do an example later on that. Now we got bar splices. So you have to specify your splices, okay? And that's mentioned in the code. And it's kind of weird because it's mentioned on the construction side, okay? Because that it tells you where do you want to. So this requirement that we have here, it tells you where do you need to specify this, where you are responsible as an engineer to specify that, okay? So you go here, so 26.611. Okay, so here, oops, yeah. So design information, okay? So here is design, you need to specify that, okay? Special seismic requirements. You need to specify the type, size, location, requirement, detailing, and embedment length and reinforcement. That's your responsibility. So you need to specify your concrete cover. That should be in your plans. Location and length of lap splices should be in your plans, right? You need to tell people where you want them, okay? So then you have your oops, I went past it now. Type and location of mechanical splices, using any mechanical splices, right? Details for construction. Oops, I went past it. No, yeah, not yet. Okay. Type and location of the end bearing. Okay. You're going to do any end bearing splices. type and location of welded splices. All these things you are responsible to specify. Okay? Corrosion protection. Okay? So things that need to be specified. These are kind of in the construction. Okay? This is important, like kind of a side thing on what we're doing. Tolerances. See, this is kind of the only place that shows some tolerances, right? There's another ECI book that has all these tolerances. But this one here tells you, right? If you have a D greater than 8 inches, your D can be plus or minus a half, right? Huh? So you're worrying about having your D at about 19.41235. No. I mean, you already got here that the guy in the field can put it half inch off of what you specify, and he's still good. Okay? Cover, same thing. Okay? Cover has also the same. So either half inch there or 1/3 of the specified cover. Okay? So you have a D greater than 8 inches. So your cover could be 1.5, could be 1 inch, and still be good, right? So the builder has this freedom to play with this. Right? Okay, so that was kind of a parenthesis on this. So let's get back. Splices, you need to splice as you can away from maximum points, maximum stresses, right? Stagger splices, that means you don't want to splice all the bars exactly the same point. Okay? Satisfy ACI 318 sections 25.2.1 and 25.2.3 when using contact lap splices. So let's look at those, 25.2.1 and 25.2.3. Okay. So 25.2.1 says, for parallel non-prestressed reinforcement in horizontal layer, clear spacing shall be at least the greatest of 1 inch. This would be this. So this is the same spacing though. So you splice, but when you splice, you're doubling the diameter of your bar pretty much, right? And so you double the diameter of the next bar too, then your clear spacing is going to be reduced. And you want to make sure that you still satisfy this. You also need to satisfy this for columns, right? So in other words, keep the same clear spacings, even with the lap splices. Okay? And then this is something that is kind of weird, right? It's non-contact lap splices. So that means the lap splices do not have to be touching each other, okay? They can be a distance apart. And that is 6 inches is the limit, but it could be the lap splice length divided by 5. So that will depend on how long is your splice divided by 5, and then 6 inches is the smallest you can have. Okay? You can also splice by welding or by mechanical devices. Okay? Now, welding is better, but remember that not all bars can be welded, so you have to be careful with that. And in either case, welded or mechanical, you have to prove that you are developing at least 25% more than the yield strength of the bar. Okay? So we have then tension lap splices. It will depend on how much steel you are providing versus is required, okay, over the splice length. So you have to look at that location that you're splicing, and you need to look at how much you're providing and how much is required at that location. Mm-hmm. If it's greater or equal than 2, and you are splicing half of the bars, then you can use class A, which means that your splice is either equal to the development length, but not less than 12 inches. This is the ideal. Mm-hmm. You are splicing all the bars. You have a class B now, which is 1.3 times the diameter, the development length, or 12 inches, which is acceptable. You have less than 2. in terms of area provided and area required, and you are splicing all cases, or no matter what case you're doing, is going to be a class B, and it's the same value as that, but less than 2 is something that we do not want, if possible. In this case, the LD that you have here cannot be corrected for the excess reinforcement. Remember that ratio? AS required to AS provided, right? We can reduce the development length. Well, we cannot do that. We're going to use the value for splices. Okay. Bundle bars shall be treated as indicated in 25617. And this one it says only is that the bundle bars are treated as the equivalent diameter, and that's what you need to use for the purpose of splices, right? Tension lap splices may not be used for bars larger than 11, okay? And so that's the limitation there. However, it's different for compression lap splices, okay? So this is tension lap splices. So no more than 11, so no 18s, no number 14s. The splice length of bars of different size, because you can have a number 8 spliced to a number 9, right? So then you have to look at the development length of the larger bar. Okay? So you have a 9 and a 10 and an 8. You have to find the development length of the 9. You have to find the splice length of the 8, right? And then you pick the largest value, okay? Whatever gives you more. Okay? You cannot have less than 12 inches. Okay. So let's look here at a continuous beam. Is reinforced with 8 number 9 bars for positive moment. 4 of these bars are going to be extended through the supports. So there are 4 that are going through the supports, right? And these bars will need splicing. Okay? So the other 4 are going to be cut. There is no problem there. But the other 4 need to go all the way to the support, but then the beam is so long that we need some splicing. We cannot have enough. We don't have enough bar. The beam is 22 by 30. That's B times H. You're going to have number 3 stirrups at 6 inches on center. F prime C, Fy. The clear side cover is 175 inches. And the clear bottom cover is 2 inches. So we're going to determine the splicing length. First, if 2 bars are spliced near the support, where your moment is 0, right? So in this case, so I'd like the end support, okay? And the other 2 bars about 6 feet from the support. That you said the end support. I think that's better, because that's where your moment is 0. Well, not really. Yeah, I don't need that. I don't think I need that. So let me back that up, because remember we're talking about positive moments, right? So positive moments, if we look at the continuous beam at the support, right? What is your moment? It's a negative moment. So your positive moment is 0 at the support. Right? So we don't need to put it in support. Okay. And then we're going to do the same, but now the bars are going to be spliced about 6 feet from the support. And at that location, the positive moment happens to be 320 kPa. Okay. So we're going to do case A first. We're going to splice 2 of the bars. So we're going to splice them there. And we're going to come here. So that's our equation, right? Where you need to find LD. And we have the factors, the old ones pretty much. All right. C sub B again, we need to check that. Distance from the center of bar being developed to the nearest concrete surface. And 2, half the center to center spacing of bars being developed. Okay. So we got this one right here. So that one is near the end, right? And so we got side cover 2, stirrup diameter, half of the bar, right? So that gives me 294. So that's from the bottom. From the side, you got 175 D sub V. And remember these two D sub V? Remember we said that the distance is not really the diameter, half of the diameter of the bar because of the curvature of the stirrup, right? And so we had to have 2 diameters of the stirrup, and that gives you 287.5. Right? Then we find half the center to center distance between bars, right? And so we did that here, 22. We subtract this side value, right? And we divide into the 3 spacings. And so we did that one right there. Right, so we got 1, 2, and 3 spacings. And we got a 542. Okay. But it says here that is of the bars being developed. Okay. Well, according to this picture, you're not doing this one. Okay. So then really you're doing 542 and 542. Right? Kind of that one. Right? So we need to multiply that by 2, and then we subtract 2 bar diameters to make it clear spacing, okay, in there, and that will give us 858. Okay? And half of that is 429. And so then this will not really control, right? So we're doing the distance then from here, to the center of this bar, and the center of this bar was the 8, was the 2 times 542, so that's 1084. So 1084 is from here to here, okay? But we want the clear spacing, okay? And so the clear spacing will be half a diameter here, half a diameter here, and 1 diameter here. So that's 2 diameters. So the clear spacing from here to here is 2 diameters. Okay? And so that's where you got 2 diameters. Okay? And then you take half of that, and that will be your number. Well, out of the 3 numbers, this one governs. Okay? And so we use C sub B, that value. 8 T sub R, we got area of 2 legs of stirrups. We assume 0.22, right? Yep. And then N equals the number of splice bars, which is 2. S is the spacing, is 6 inches. Okay. In there. Now we're using 2 legs because remember the one that controls your side surface, right? So that means your cracks are horizontal. So there are 2 legs that are crossing your horizontal cracks. So that's what we're using, that one. If this one with the control, we use only 1 leg. Mm-hmm. All right. So we got that 40, our 8 T sub R, spacing, number of bars, right? Being spliced, and this will be 112.8. So we put it here in the formula. 320 exceeded the 2.5. We can only use 2.5. So we use 2.5. That gives us this number. Multiplied by the diameter of the bar, it gives us 32 inches. That's greater than 12. That's the minimum, 1 foot. So 32 inches. Okay. We cannot correct for the ratio required or provided. However, we still need to find the ratio, but the other way around, provided over required, right? Because we need to go into that table for deciding what kind of formula we're going to use for lattice splice. Well, AS provided over AS required is greater than 2. How do I know that? Positive moment of the support, 0. How much area do you need? 0. So if you put 1 bar, you already have more than twice 0, right? So in this case, we are greater than 2, no matter what. Okay? And we are only splicing 2 out of the 4 bars, so that means 50%. So we're allowed to use, according to the table, class A splice, where the splice length is equal to the development length, right? 32 inches, and cannot be less than a foot. So that's it, 32 inches. That would be the splice. If we splice at the support. Okay. Now, let's splice 6 feet away from the support. Well, first I need to find my area of steel that I need. Why? Because of this. Okay. What is required? What is provided? So, I find my moment. It was giving us 320. We do our formula with quick ratio. You don't need to have exact area, okay? Quick. Okay? So 0.9D, approximate value, sounds good. 292. Okay? So you can use that. I can use another there. Okay. So I got that value. Where did you get the 294? You were saying, oh, right here. Remember, we found it, right? This is the distance from the bottom surface, 294. So my D is going to be my 30 inches minus the 294. Okay. Multiply by 0.9. So that's an approximation. You know this area is approximate. So we got that area. That's 4 divided by 292, 137. You can improve the calculation, right? But it's going to be less than 2. All right? So that means less than 2 and 50%. That's the bad case, right? And so class B is placing 1.3. So now we're going at 41.6, which will be really 42 inches. So if I splice 6 feet away from the support, I need 42 inches. Now, what happens if I splice all the bars of the support? That would be case B. Yeah? So now the spacing center to center changes. Okay. Now we got the 542 minus 2 times the diameter of the bar, right? And that leaves us only with 316 now. Mm-hmm. And half of 316 is 158. Mm-hmm. And so now 158 controls over the other case. Okay, so you still have a horizontal splitting, but it's controlled by the clear spacing between bars. So C sub B then is going to be 158. Your Lexus are going to be 2. This is the same, 4. Spacing is the same. And so when we get here, now we get a value 173. So we can use that number. So we put it here. We got a 41.1. And then we multiply by the diameter. So we need 46 inches of splice. Some people may round this to 48, right? And that's what we have. But now we still need to look at the support, right? Again, in the support, we don't need any area, so anything that we put is greater than 2. So by way of splicing 100%, so we need to multiply by 1.3. And so that makes the 160. So now 60 inches will be your splicing length. You are doing it 6 feet, or you splice all the bars at the support. So that's why this is how you play, right? Do I splice all my bars? Do I splice half of the bars? Do I splice 6 feet away? Where do I splice my bars so this becomes economical? And so that's kind of the ideal thing that you need to look when you're doing your designs. Okay? In most cases, I mean, people just splice at the supports and splice a couple of bars, okay? Or half of the bars. I mean, that's kind of the easiest way to handle this. The compression lap splices have all these formulas now here. Yeah, I think that one is just the equation number. I don't know if I can fit. Oh no. Yeah, I don't think it fits anymore. That's what it is. So this is the equation number 1113. But now they added, I mean, this thing about the 80s. Okay? And so be careful again with that one. That has been added to include this. This is also a very special note that you don't want to forget, that if your concrete is less than 3000 psi, whatever you find here has to be multiplied by 4/3. Okay? Compression lap splices may not be used for bars larger than 11, so it's similar to the tension bars, but there is exception here. And the exception, what it says pretty much is that you can splice some smaller bars, like a number 11 to a 14 or number 8 to that, right? And so you can do that. Okay? And because you're splicing bars of different size, you also need to satisfy this part right here that says that your development length is either the compression development length of the larger bar or the compression lap splice of the smaller bar, similar to the tension. Okay? And of course, you cannot have values that are less than this 12 inches, and LST. Okay? So that's your limits. Okay? So when you're doing columns, which is what you're going to have this compression, right? You will have to satisfy lap splices in compression. Now be careful that not all columns may have bars in compression, some may be in tension. Okay? If the compression reinforcement has enough ties where you satisfy this requirement, H being the dimension you're looking at and S is the spacing of your ties, in both directions. Okay? So you have ties with an effective area no less than this in both directions, then you can reduce it by 83. So you can multiply by 0.83. Okay? You have spirals satisfying section 2573, you can reduce it by 0.75. Okay? But you can never go below 12 inches. Okay? Now, I don't know if they forgot about this right here, because remember that now we have added this one for the 80, which the limit is not 12. It used to be 12 for everything. Now is this one, okay? So I think that applies here. So it should be 12 or LST if you are doing 80. Okay. So how does it, now you start having bars in tension, right? And so now you're looking at class B splices if more than 1/2 of the bars are spliced at any section. Class A, you are doing half or less at the section. So that's between 0 and 0.5. Now you go past half, okay, you have to use class B. Okay? And this has to do with interaction diagram. Remember? The interaction diagram, very nice, right? Right there. Right? So bars are in compression from here to here, right at this point. At this point, you start having tension in your bars. Okay? So you are here, then you will use class A if you are doing half of the bars, and class B if you are doing all the bars, right? Or more than half, right? So that's that one. And then from here, you are in class B, okay? Class B splices. So that's also why your interaction diagram is good, because then you will know, right? All your bars fall here, and this corner, well, yeah, all your columns are in compression. But you have points bar that have here and there and there and here and there. So now your lap splices are not the same for all your columns, right? Your columns are all safe because your design is within the interaction diagram, but your lap splices may not be the same, all right? So let's look at one example here. You have a column, you're going to lap splice, and in this case, you're going to lap all the columns. Okay, all the bars are going to be lap splice. So number 8 bars to number 9 bars. You're going to use number 3 ties, no special confinement. And you got your strengths given. And first, you're going to use just the regular ACI spacing. And then you're going to use ties at 9 inches. Now, what is this one right here? This is something that I've repeated already in the columns, right? And we're going to see here, these are the requirements for spacing to control the stability of the bars, to prevent the buckling of the bars. So the S maximum that you get here is for stability. It has nothing to do with your shear. Okay? So we got that 16 times the diameter of the bar. That's the number 8, 16 inches. 48 inches times the diameter of the tie, 18 inches. The smallest dimension of the column is 14, so 14. Okay? So that will be the spacing, and that also satisfies the spacing for aggregate, so we're good. Okay? So because we're doing 2 different bars, we need to find the development length of the larger bar and the splice length of the smaller bar. Okay, so we look for the development length of the number 9. So we got the values, strength, the correction factors, no special confinement, okay? And so we put it here in the formula. We get 20 inches. We use the second formula. We get 20.3, very similar, but 20.3 is larger, so we'll use 20.3. Okay? And this is greater than the minimum, which is 8 inches. So that's one part. Then I do the compression splice of the number 8, the smaller bar. So again, I go to my correction factors, like this B, use the formula, and I find that I need 30 inches. So 30 inches now is bigger than my 20.3, so out of the 2, I pick 30 inches so far. Okay? So far I got 30 inches. All right. One thing you should be asking, hopefully you are asking, but maybe not. This formula, right? Where does it come from? Oh, don't forget, we have 3 formulas that we have now available for that, right? Right here, less than 60, you use that one. 60 to 80, you use that one. And greater than 80, you use this one. Okay? But these two are the same, but the difference is what is the minimum. Okay? All right. So we have that then. So that one comes from there. So that's that formula, less than. So we satisfy the 12 inches controls. Now what we're going to do here is try to understand, right? Try to understand what is this requirement, right? 0.83 when this happens. So what exactly they mean by that? Okay. So we're going to use now our information and see how that applies. Okay. So we come in here and we say, okay, we have to check in both directions, okay? So ties in each direction must not be less than 0.0015 HS. So I'm going to use the long direction. My H will be 18 now, okay? So 18, long direction. So let's look at long direction. Okay, there is my long direction, right? Okay. So these are the legs that I have. Okay, long direction. Okay. If I go in the short direction, my shear only has the other legs. Okay, so only 2. So you have to be careful on which direction you are looking at your shear. Okay, so so here I'm using 4 legs of ties, and the other one it will be 2 legs of ties. So 4 legs in the 18 direction. I know. You will be complaining already. Wait a minute, there is no 4 legs in there, only 3. Yeah, that's because I missed the other line here. So remember, I'm putting a stirrup that goes like this, and then I'm putting another one that goes like that over here. Okay, so let's make it right, because so you don't have to come back and then tell me, wait a minute. So I think what happens is you just move. So you have the other leg there. Okay, and so make sure that we get that one. Let's make it the same color. Make it a little thicker. That's about right. Okay. All right. So there is the other leg, and so we got the 4 legs. Okay. So 1, 2, 3, 4. Okay? 18. And so now we're good. So 4 legs multiplied by that 0.44, and so that's my AV. The require, this value is 0.0015. The H, and that depends on the direction I'm looking. I'm looking in this one, so that's 18. The spacing, which we said based on the stability, right? Based on the stability, the spacing is 14 inches. All right. So if I just use that as my spacing, then this is what I have. So I need then a require of 44. Excuse me, my AV is 44. My require here, which is this one, is 0.38. I exceeded that, so I'm good. Okay. So I'm satisfying that. Okay. On this one, on the other direction, is 14. Now, in that direction, we only got 2 legs. Okay. So you apply your shear. Now you're applying your shear this way. It only crosses that leg and this leg. Okay. So only 2 legs. So 2 legs in that direction. So that's 14. So we got 2 times that, 0.22. Multiply here. My require is this number. I need 29, but my value is less, 22. So it's not good. I need to have more than the required, right? So it's not good. So I cannot use my 0.83. So my length remains at 30 inches, right? Which is greater than the 12. And comparing the two numbers that I got, my 30 inches and my 20.3 that I found, I picked the largest, and it's 30. Okay? So don't forget that this one, 20.3, is this one, okay, that we found here. Okay. So that your development length in compression in there. Okay. So your compression, your development length in compression. All right. The one we're correcting is your splice length in compression, okay, which is the 30. Okay. So those are the differences between these two numbers. Okay. So this is the splice length and the compression. That's the one that is affected by the 0.83. But this one not. That's the 20.3. Okay. So we're comparing the two and there. Now, what happens if I change the spacing not from the 14 that was required for stability, but now I had to put it at 9 inches because maybe my shear is requiring 9 inches, right? So I do 9 inches. So pretty much everything remains the same. The only thing is that now I can check at this 30 again, right? And I look at the direction on the 18, right? And that looks good. I mean, this is 9 now, this is low, so I get 0.24 now. I'm doing great there. Now with the 14, right, I have my AB at 0.22. My AB required now, because of the 9, becomes 0.19, and that one now is also greater than that. So we're good now, okay? So we are satisfying these in both cases, right? And so we have it, okay? So now we're good, both cases, so I can use the 0.83. So my 30 now becomes 25, which is greater than 12 still. So now I compare the 25, needs to be compared to the 20.3, so still 25 governs, my splice will be 25. Okay? So I got a little reduction by changing my spacing of the the ties. Yeah? Now what happens if you have a lapis splice in tension? Okay? So now your bars are at 0.5 Fy. So we do the same thing, number 8 bars are spliced to number 8 this time. So we don't have to deal with that different kinds of bars. Right? So tension, we have to use the regular development length in tension. Okay? So we do that. We find our values, right? So everything is a 1. C sub B is greater than 2 inches, and KT sub R is larger than 0.5. So we can assume that this is really a 2.5 based on the values given. Okay? And so we find our value, that's 26.83. We multiply by the number 8, so 26.3. Because it's a tension and we're splicing all the bars, we need to multiply by 1.3. So 35 inches, we're going to use 3 feet. Okay? So tension, then you had to use the development length for tension. Okay. Okay, so let me stop here.